How have engineering safety factors evolved from rules to science? Imagine building a bridge or designing a car that could fail unexpectedly. How do engineers make sure these things are safe? It all comes down to safety factors. In the beginning, safety factors were simple numbers. Engineers would just multiply the expected load or stress by a certain factor, like 2 or 3, to add a safety margin. These numbers were based on experience, tradition, and conservative guesses. They were easy to use but not very precise. For over 150 years, safety factors mainly served as a cushion. If a structure was designed to hold twice the expected load, it was considered safe. But engineers knew loads and materials varied. Some materials were weaker than expected, and loads could be higher than predicted. So, safety factors acted as a buffer against these uncertainties. As engineering advanced, engineers started to see that these safety factors were not enough. They realized that uncertainties came from many sources, like material inconsistencies, changing loads, and aging structures. Instead of fixed numbers, they began to analyze these uncertainties more carefully. They used statistical methods and probability theory to understand the chances of failure. This shift led to what is called limit state design. Instead of applying the same safety margin everywhere, engineers began to consider different failure modes. They calculated the likelihood of failure for each part of a structure and adjusted safety factors accordingly. This made designs more efficient and reliable. Modern safety factors are now part of a scientific approach called load and resistance factor design. Instead of fixed numbers, engineers use data about materials and loads to determine specific safety margins. These are called partial safety factors. For example, the safety factor for steel might be different from that for concrete, based on their properties and how they are used. This evolution also includes insights from biology. Biological structures, like bones and shells, show design margins shaped by evolution. These natural safety factors balance strength and flexibility, helping organisms survive. Engineers now use this idea to design products that are both safe and efficient. Today, safety factors are based on real data and probability. They help predict how likely a failure is and guide engineers to make safer products. For example, in aerospace, safety factors are carefully calculated to keep weight low while ensuring safety. In automotive design, reliability is improved by understanding how different parts might fail over time. This scientific approach to safety factors means we can prevent mechanical failures more effectively. Instead of guesswork, engineers now relying on data, testing, and analysis. This makes our bridges, cars, and machines safer and more reliable for everyone.